Hey, this is Travis, and today I want to tell you how you can identify your target users for product design purposes with something called K-Means clustering. And this is a technique that the field of market research has used for decades now. And in the market research use case, they call it a market segmentation. You start with an overall market or group of customers. So let's say a random representative sample of the US population. And then you apply a clustering algorithm to specific variables that you collected through a survey to group these customers into groups with one another. So the customers within one group are highly similar to one another, and then the customers between groups are highly dissimilar to one another. So you get highly dissimilar customer groups, but each group is homogeneous, and it's thought as homogeneous in terms of its needs and its wants. So this helps us from a product design perspective, where we can find we can find segments that have perhaps niche product needs and optimize our product for their specific use cases. It also has appeal for marketing, messaging, and advertising targeting. Perhaps each of these groups have different attitudes from one another, and different market messages will resonate differently with them. And then also we can see the demographic information of each of these groups and their interests, perhaps the devices that they own. And this helps us from an ad targeting perspective, especially when you think of ad platforms like Google, Facebook, these ad targeting platforms. We can have more precision when we're targeting our ads. Did I say targeting enough? Okay. So I just want to go over the three main approaches to a segmentation. Again, because when you think of a segmentation, you have to think of how you want to define the segments. When you create a profile for each segment, what is going to differentiate each segment from one another? And these are called segmentation variables, or what I now refer to as clustering variables. These are the variables that we're going to apply our clustering algorithm to, and this algorithm is going to find differences. It's going to group respondents based on different answers to these questions. So the first category is demographics. Age, gender, income, education. Those are some main ones, obviously. Usage and behaviors. Like what is their current usage of the category and product usage? Maybe it's a frequency rating from 1 to 7. I'll talk about this in a second. And then attitudes, interests, values, personality. These are general things, but they're overall approaches to how you would define or differentiate segments from one another. So in this case, I'm actually going to take a hybrid approach where I use two sets of clustering variables. The first is going to be product behaviors or product usage, and the second is going to be attitudes. So in this example, we're going to be creating a decentralized wallet. And what we want to do is understand the current users of the blockchain apps, decentralized apps, and then also decentralized wallets. So this is going to be our overall market that we're studying is decentralized app users. And we want to segment this market into smaller user segments so that we can find potentially niche groups that have currently undermet needs and optimize a product for them, and hopefully attract some early adopters, get some initial revenue, and then transition more to a growth stage from there. But that comes later. First, we need to attract early adopters, and we can do this by zooming in on a specific segment in the market and really focusing on their needs and delivering value for them. So as I said before, we have two sets of clustering variables. One is an attitudes approach and the other is a behavior approach. So for attitudes, I ask, how important are the following features for a decentralized wallet? And then from a scale from 1 to 7, I get an importance rating for each of these. Buy crypto with a card, access to financial tools, limits protection, decentralized token swaps. In other words, how important are these features to have for you in a decentralized wallet? And then the next set of clustering variables is the behavior and usage one, and it is how often do you use the following DApp services. So we're getting current category usage on things like lending crypto, borrowing crypto, trading crypto derivatives. These are obviously DeFi use cases. Decentralized crypto exchange, private equity tokenization, health, insurance, IoT and Oracle systems, digital identity. We want to know how frequently and how often they're accessing these services. So again, these are our clustering variables, and these two sets make up 29 total clustering variables. What we're going to do eventually is feed all of them into a clustering algorithm, and this algorithm is going to group users based on differences on these clustering variables. So in each group we should end up with users who have similar DApp usage and decentralized wallet attitudes to one another, and that these groups are going to be different from one another in their needs and DApp usage. So this is going to be very interesting, and it will help us with product design, because eventually we can find a target segment, someone who we think, or a group that we think is most likely to be an early adopter to our product if it fits in with our initial product vision. So going down here, I'm just showing you an example of the survey question that you would use in Qualtrics. This is, again, 1 to 7 scale from extremely unimportant to extremely important for the features within a decentralized wallet. And then the next is DApp usage, and we're getting frequency. Again, 1 to 7 rating, but frequency. So from 1 day per week or less to once per day or more for each of these. Very cool. So they're going to go through and rate them. And anyone who is used to surveys will know when you ask a Likert scale question, the raw data is actually a numeric variable. So if a respondent selects this, then it's going to be 1, 2, 3, 4, 5, 6, and 7. So we're going to get numeric vectors for each one of these clustering variables here. And we're going to end up with 29 of them, of course. Now, I have talked a lot about our clustering variables. These are the 29 variables. To talk a little bit about external variables, these are variables that we still want to collect in the survey. We still want to ask these questions. They're just not going to be used in the segmentation or for the clustering. They are external to the clustering, and that's why we call them external variables. And these are things like demographics, technographics. Let me see, I had a list here. Psychographics, kind of like personality, and then media usage, like how can we reach them and how should we communicate to them, and what are their social media interests. So these external variables are really important because once we have the segments that are defined on the clustering variables, we can then profile the segments with this extra information that we're getting from external variables. So it's really important, and it will show us how to communicate and reach this audience. Yeah. And just a note, and this is kind of technical here, the main analysis in a segmentation is to compare segments between one another. So on the clustering variables, we know that there are going to be differences between the segments on the clustering variables because we fed these variables into the clustering algorithm, and it is the mandate. It is really the sole purpose of this algorithm to create these differences and create these groups or segments that are different on the clustering variables. The external variables, not so. So it's a really good sign, actually, if external variables have correlations with each of the segments. So demographics is a type of external variable we might have. Obviously, we're going to get their age, gender, income, education level when we give them this survey. And it's really good sign if demographics correlate with specific segments. Maybe we have an older segment, maybe we have a younger segment, middle-aged segment, maybe we have a segment that uses mobile devices mostly, and then the others use PC and Macs, right? So it's a good sign that these are correlating with one another because it gives us an external validity. It gives us more validity to our clustering solution. Anyway, that's a technical note, and don't want to get too much into that. And now I'm moving on to sample size here. I know that for every study, we're, as researchers, very interested in what sample size to use. I think for segmentations, it's definitely a larger sample size that you need. So I would recommend like at a minimum 500, but really like 1,000 for a minimum. And it's really common to see big segmentation studies, especially if a company has quite a bit of money, to have sample sizes of 3,000 to 5,000 respondents. It's just how it goes. And the reason is that the total sample size is your total market. And then when you create the segment, each cluster, the total sample size is going to be divided into these segments. So if you start with 1,000 respondents, but you create 10 segments, then on average, each of the segments is only going to have 100 respondents. This might be okay for your purposes, but at 100 respondents, it's starting to become a small sample size. And again, the main analysis in a segmentation is to stat test differences in differences on clustering variables and external variables between the segments. So you need larger sample sizes to have more precision when you're stat testing these. So it's just something to keep in mind. And I talk a little bit about something called a power analysis down here that you might want to take a look at if you're really serious about designing one of these studies. Finally, let's talk about inferential statistics. This applies to any large sample quantitative study that you're doing, but especially for segmentation. So what inferential statistics is we want to understand a population and make claims about it. In this case, the population is blockchain users or users of decentralized apps. How many of them actually exist? The population is every single person in the world that meets this criterion. Probably a lot, potentially millions, but definitely hundreds of thousands. It's not feasible for us to survey each one of them. That would never happen. We wouldn't have enough money and we wouldn't be able to reach everyone. So the beauty of these surveys and something called inferential statistics is that we can make claims about this population by randomly sampling people from the population and then giving them this survey. So let's say that the population size is 250,000 people worldwide, but we give this survey to 1,000 of them, and they were randomly selected out of the population. Now we can make claims about this population. Now there's going to be some error involved, but still the overall premise stands that we can say things about this population, and that really is kind of magical. Anyway, the main point is sample size comes into play with however much statistical confidence you need in making claims about this population. Obviously, larger sample sizes are going to be better and lend more statistical confidence to your claims about the population or your inferences, right? Hence, inferential statistics. Another thing that is very important is random representation. We need to randomly select participants out of the population. If there's some bias in recruiting these participants, then it's going to skew the data somehow based on that bias. Of course, it's impossible to get rid of these biases entirely, but it's just something to keep in mind, and it's an entire field that you should study and think about if you're interested in this kind of research. If you're just starting out and and there's a lot to think about, then the survey platforms like Qualtrics or recruiting agencies, the agencies that are actually recruiting the users to take these surveys, they will help you with a sampling plan. Okay, now we move on to the actual segmentation analysis. As I said before, we have a data frame with 29 clustering variables and a unique respondent identifier for each respondent. And these are, again, Likert scale ratings. They're numeric, and they range from 1 to 7. Now, actually, in reality, we would also have external variables in this data set, but I left them off for simplicity. Now, as I said before, in previous videos or chapters, depending if you watch my YouTube channel or read the book that I'm publishing, there are response biases when it comes to using a Likert scale. Some respondents just systematically give low Likert scale ratings. Others give slightly higher, and then others always give high, consistently give high ratings. This is a problem when we're trying to cluster and then compare the Likert scales between one another. So what we need to do, and what we've done before, is standardize the data. In this case, we subtract the average Likert score that a respondent gives across the 29 clustering variables. We subtract that from each one of their Likert responses. So this centers their responses. It is centering at the respondent level. And this makes their Likert scores comparable to one another, and so it kind of reduces the bias imposed, or the negative effects imposed by the scale use bias. Cool. And this is the data frame that we have, and this is actually what we're going to input into our clustering algorithm that we'll get to in a second. Before we do that, we can check data clumpiness, or the degree to which points or respondents are randomly spaced in this 29-dimensional space, which I'll talk more about a little below. But basically, we want to, there's a test called the Hopkins statistic that will tell you the quality of the clusters that exist in the data. It's just a diagnostic that you can run. Anything from 0.50 or above, it seems pretty random, and it's basically telling us that there are not really reproducible or good clustering patterns in the data. Anything of 0.35 and below, one statistician told me that this is his threshold right here. Anything from 0.35 and below, when he can usually get a good segmentation clustering result from the data here. And it's a good sign because we are below 0.35. We come in right under 0.31. So that's good. And that's called the Hopkins statistic. Next, when we actually cluster using a machine learning algorithm, we have to set some parameters. And by far the most important parameter is the number of clusters that it searches for, right? So there are statistical methods that estimate the number of segments in the data. This is called the elbow method. This is called the silhouette width. So elbow method is, you look at where it starts to bend, the elbow of this curve, and that's either at a 2 or 3. Silhouette is 2. It's recommending that 2 is the best number of clusters in this data. And then a gap statistic recommends 2 as well. So our statistical measures, or we're trying to estimating the true number of clusters in the data, is like 2 or 3, okay? In actuality, in a segmentation, really what we're going to go for is the best story for our business and what helps us most with product design. So these statistical estimates are good, but if we end up with like a 4 or 5 segment solution, and it's just so much better at defining specific segments that we need, and we feel that it tells a better story about the market overall, then we're going to go with that. It's more important to use your intuition rather than rely solely on a statistical estimate. Now, ideally, both of these align, right? If the 4 segment solution is intuitive to you and the estimates are also suggesting 4 segments, and that's the best, but in most cases, that's not the case. And segmentation is an iterative process. So what I recommend is always running a 2-segment solution, 3-segment solution, 4-segment solution, all the way up to 10-segment solution. No matter what estimate you get for the clusters, you should create all of these different solutions and then manually look through each one in crosstabs to find which is telling the best story in terms of differences between segments on the clustering variables. What is making the segments pop the best, which solution. And I'll show you that in a second here. But now we're to K-means clustering. This is the machine learning clustering algorithm that we're going to use, and it's the most simple. And K-means clustering clusters respondents based on distance from one another. So we can think of, let's just go to our human intuition here and think of distance between points on a line, right? A and B, and we can calculate that distance. That's one-dimensional distance. Two-dimensional distance is we have a map and we can calculate points between A and B, right? And then three-dimensional, obviously, here's a depiction of three-dimensional distance, or three-dimensional clustering here. And again, you can calculate it X, Y, Z. There are, I think it would be there's some Euclidean distance equation you can use for that. Now, this is our intuition. Now, we are using 29 clustering variables. So from the perspective of linear algebra, our respondents, each point or observation, but that corresponds to a respondent, falls into 29-dimensional space because they are defined on 29 clustering variables. Now, we can't imagine this with our minds, but it's still very easy to calculate distance between these respondents. So just know that that is what's happening in the background. And here's an example of clustering in three-dimensional space, right? Obviously the colors correspond to the different clusters, and they're being grouped together based on their distances from one another. So let's talk about actually how the K-means algorithm works. It's super clever, and I'm pretty sure that this is how most distance-based clustering algorithms work, although there are others like hierarchical clustering. So what K-means does is, again, first we have to define the number of clusters that we're going to do. I'm recommending that you do 2 clusters through 10 cluster solutions, but let's say we start with 3 clusters. Then you initialize the cluster centers. So the algorithm randomly selects 3 points in this 29-dimensional space to initialize the cluster centers. Then we calculate the distance between each of the cluster centers, or we calculate the distance of each of the points from each of the cluster centers, and we assign each of the points to the closest cluster center. So these points here, these red ones, are closest to this red cluster center right here, so we assign them to that, right? These green are closest to this, and the blue closest to this. Now, in the next step, we average the points within each cluster and then move the cluster center to that average, right? And so you can see in each case that these cluster centers are being moved into the center of the points that were just assigned to it. Since the cluster center is moved, now we recalculate all the distance of all the points from all of the cluster centers again, and then assign, like we did in a previous step, assign the points to the closest cluster center. And again, we come back to, now that we've assigned new points, we have to recalculate cluster centers, and we do so, and we continue this process until the cluster centers stop moving a material amount. So that's pretty interesting, I think, and that's how we discover clusters or respondents who are similar to one another in the data. Very interesting. As always, fitting a machine learning algorithm or statistical model in R is so elegant. It's just a simple line, and here is a 3-segment solution, 4-segment solution, 5-segment solution with changing the centers parameter in each case. And end start is we do 30 runs of each one. And then we choose the run that is most similar to all the other runs. And this helps with reproducibility and reduces the effect of outliers. Anyway, we can get further into that, but I explain it more here, so you can read that. And then now that we have the clustering solutions, we're finished. And it's really simple. What the clustering does is it assigns a segment to each respondent. So the final output for a cluster solution assigns a segment membership to each UUID. And this is the data frame that we use right here. Next, we can summarize this and look at how many respondents got bucketed into each of the segments, right? So segment 1 has 118 out of 500, 2 has 146 out of 500, 3, 236 out of 500. And then, we can see that here. And then just a note for 5 segment solution, see how some of these sample sizes are getting small, particularly segment 4 right here is already at 37 respondents. So that's no good. It's going to be hard to find statistically significant differences between segment 4 and some of these other segments because it has such a small sample size. So this is what I mean by starting with a large sample size. And now, again, each clustering variable is numeric, so we can summarize this data set by segment. We can calculate the average Likert rating for each of the variables by segment, right? So here's segment 1, segment 2, segment 3, segment 4, and we should see clear differences already between these variables. This is super low, this is relatively low, this is relatively high, this is somewhere in the middle, and this is higher, right? This is what our clustering algorithm did, was it searched for differences, it grouped people together with similar Likert scale ratings, and so the averages on the clustering variables between the segments are different, and that's what we're summarizing here. Now, to actually do an analysis in R is going to be a pain. So I don't recommend doing it here. This is kind of an initial check. What I do recommend doing is giving this data frame of UUID and segment to your crosstabber and running crosstabs for each of the clustering solutions that you ran. All right, so you start with a 10 clustering solution, you go all the way up to a 10 clustering solution, and your tabber is going to give you back, or should give you back, 8 Excel files, and you're expecting the segments in the columns and then each of the questions in the rows, right? So your clustering variables are going to be in the rows and your external variables will be in the rows, and you can stat test between them. And this is what we're doing right here, right? So we did a 3-segment solution, 4-segment solution, 5-segment solution, and we're highlighting statistically significant differences between a segment and total. Segment versus total, segment versus total, right? So let's look at this 4-segment solution and just a, what do they call it? A spoiler alert. we go with this 4-segment solution at the end. This is what we choose for the final run. And so you can see here that segment 1 is over-indexing on 1, 2, 3, 4, 5, 6. These 6 decentralized wallet needs. They're over-indexing on that. And then the others are under-indexing here in the red, and some over-indexing here on specific features in the green. And then here's the second set of clustering variables, and we can see over and under indexing here on their usage of these DApp services. So very cool. And we can see that the clustering algorithm worked and our segmentation worked for the most part, right? I know we haven't gotten into the story about each segment. We need to look deeper and try to figure out what it's telling us, but we can definitely see differences. We can definitely see that our segments are differentiated from one another. This is great. Cool. Okay, yeah, and just a note here again, these are our clustering variables, and you would also have rows down here for the external variables, and it's important to look at differences between those. And remember, it still is going to be great if you have differences between the segments on the external variables, something like demographics, right? Can we say that solution 1 is older than solution 3 or 4, right? Or is the oldest out of all of them? This would be great. Cluster reproducibility. This is a diagnostic for the quality of clusters. It's very rarely reported to stakeholders, especially non-technical ones, but it's something that you might want if you're a technical person and interested in this kind of thing. What a clustering reproducibility is because the K-means is somewhat random. We start with random starting points. So one run is going to be slightly different from another run. So that's what we do. We do 2 runs and we compare the overlap between those 2 runs. So a 100% overlap means that the clusters are 100% reproducible, right? And anything less than that means that it's less reproducible. There's some error involved, or the clusters aren't as precisely defined, and you're never going to get 100% reproducibility. But yeah, this is a way to check for cluster quality. So again, we do 1 run and we do a second run, and then compare the overlap between that. I do that 250 times, and then I average the overlap over those 250 pairs. And that is what I use for the reproducibility score. 3-segment solution, 99% reducible, that's awesome. 4-segment, 95% reproducible, awesome. 5-segment, slightly less reproducible, 0.8, 80% reproducible. But all of these reproducibility scores beat the random chance, the random chance situation. Like a 3-segment solution has a 33% chance. So obviously this random chance, this 99 beats the 0.33, right? 0.94 beats 0.25, and then 0.8 beats 0.20. Now we're moving on to the actual deliverables you're going to give to your respondent or to your research stakeholders. The 2 main ones for a segmentation are I'm just looking at the time here, are the market size. So you have a pie chart of your entire market. In this case, it's D-app users or decentralized app users. And then the size of the segment within that total market. That's the first deliverable. And the second deliverable is a profile for each of the segments and showing the key differentiators between each of the segments on the clustering variables and external variables. So we have D-app hobbyists here, and we named him that, enjoys exploring and trying new and interesting use cases of D-apps. I named him that because they say that they want this feature plus 20% compared to total. So it's a huge over-index compared to total on a want to explore D-apps in their decentralized wallets. And then this is further backed up by their usage of D-apps. 1, 2, 3, 4, 5, 6, 7, 8. So on 8 of the 20 D-apps, look how much they over-indexed on things like social platforms, gamble and prediction. I know gaming was another one. So it's really interesting. And these next 2 segments, mobile DeFi youngsters and DeFi traders, well, they actually under-index on the other D-apps, on all these other like niche D-apps, but over-index on the DeFi D-apps. So these are people who use DeFi more often than the other segments, and that's why they're named accordingly, right? Mobile DeFi youngsters are savvy young investors searching for alpha in the wild west of DeFi and gaining access while on the go. DeFi traders, they're slightly older, they're more professional, and they seek, again, here are these clustering variables down here, they seek more traditional or financial-based news like CoinDesk and traditional finance news. and over-index on trading crypto here, or trading crypto derivatives. So yeah, they're older, they're more professional, they're interested in trading crypto, so I call them DeFi traders. Use DeFi as financial professionals and who want robust trading capabilities. And then DApp altruists, they under-index on these DeFi feature needs, but over-index again on Explore DApps. And specifically, they are heavy users of health, insurance, and IoT/Oracle system DApps. And I saw down here on an external variable that they really highly over-index on entrepreneurs. So I'm saying that they're DApp altruists. They're wanting to create products in the health, insurance, and IoT DApp space. And yeah, so want to drive societal change through blockchain and health, insurance, and IoT use cases, right? So this is just the basics of how I created this segmentation story based on external and clustering variables. Yeah, let's see. And so I show my rationale more down here. It's more thought out, and so you can read that if you want to see the rationale there. But this is an example of how you interpret a segmentation. Now that's basically it for the segmentation and for clustering. And now we move on to something called a typing tool. And this is a tool that allows you to extend the segmentation. What a typing tool does is it takes an input of answers to the clustering variables, and then it gives you the segment assignment. So let's say that we talked with these people, we created the final 4-segment solution, and everyone loved it in our company, and we're making great products based on it. Now we want to learn more about the target segment, which we'll say is DApp hobbyists. And so we want to recruit the DApp hobbyist segment for future qual and quant studies. Well, how do we do that? What we do is we place the clustering variables into our screening surveys and then use these typing tools to take their answers, put it into the typing tool, and then get the segment assignment out of the typing tool. So then we can say we only want to talk with people who are assigned to segment 1. These are DApp hobbyists. So again, this is a way to extend the segmentation. And what a typing tool is in the background is something called a classification algorithm. So we clustered, and now we are classifying new respondents, trying to assign them to these final clusters. The first step in creating a typing tool is to get the variable importance for each of the clustering variables in determining segment assignment. And we can do this with something called a classification tree. It's an easy call called var imp. We call it on the tree. And it gives us a rank ordered list. Out of all 29 of our clustering variables, it ranks orders from most important to least important, these clustering variables. So that's important. Now we fit a classification model. We have to create a classification algorithm which the typing tool uses to classify or assign new respondents to these segments. So we do this in typical machine learning engineer fashion. We have our total data set, and we need to break it into a training set and a testing set. And so we do an 80-20 division. We take 80% of the respondents for training, 20% for testing. We train the classification algorithm using the training respondents, and then we test its accuracy using the test or out of sample respondents, the 20% over here. So the actual classification algorithm that we use is called a linear discriminant analysis. And I want to look at a linear discriminant analysis using anywhere from 2 predictors, the top 2 predictors, which are the top 2 clustering variables, the most important ones that we found above, to using all 29 clustering variables. And my hope is that we can get an accurate classification algorithm with fewer than all of the 29 clustering variables. Because If we use all 29, we have to put all of those questions into every other survey to extend our segmentation. But let's say that we can get the top 12 variables makes for a great, really accurate classification model. Then we only need to put 12 questions into our future surveys. So it's a matter of resource saving. Anyway, I'll let you look at this, but this for loop runs through everything that I said. It creates it fits a classification algorithm to the top 2 predictors, then the top 3 predictors, and then calculates the accuracy. Then the top 4 predictors calculates the accuracy. Then the top 5 predictors calculates the accuracy. And it keeps doing this until it gets to 29 predictors. So this data frame right here shows, a 2 variable model through a 29 variable model, and it shows the accuracy of each one, right? So it's going to be counting up, right? Because the less variables that we have, the lower the accuracy of the classification algorithm. And we see here that the top 11 variables gives us 80% accuracy, which is considered it's kind of the industry standard for a typing tool. You want at least 80% accuracy. So what we're going to do is use the top 11 most important variables, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 right here, right? So we're going to use these top 11. I was pointing, but you can't see my finger. You can only see this cursor here. And we're going to fit a final classification algorithm using these top 11 variables. Cool. So we do that. Oh, wait. Okay. Top 12. I guess I chose the top 12 for some reason. Okay. That's fine. So we use the top 12 variables. We fit the final, we fit the final model here. And the reason that we use the linear discriminant analysis for classification algorithm is because it gives us a linear equation for the likelihood of segment membership. So right here, this column 1 is for segment 1. We have a constant, and then we have a coefficient that you multiply each Likert scale response by, and then it gives you a likelihood that respondent is in segment 1. Same for 2, and same for 3, and same for 4. So what the typing tool does is it takes their responses to these 12 variables. It calculates the likelihood that the respondent is in each of these segments using these linear equations, and then the linear equation that outputs the maximum or the greatest value out of the 4 is the segment that the respondent is assigned to. So here's just an example of the linear equation for segment 1 likelihood. You got your constant. Here's the first coefficient right here, and you multiply this vector for this clustering variable, right? And this is going to give you number, and you're trying to find out of the 4 numbers which has the greatest score, and you assign the respondent to that segment. And usually you create these in Excel. So this is how you create a typing tool. And so just to summarize, guys, we started with a total market of users. These are DApp users. And we wanted to understand specific segments within this market who have unique product needs. They use different DApps. We wanted to understand the market by breaking it down into these similar segment or into users who are similar to one another but different from the other groups, right? So this is the segmentation. And we base this on their decentralized wallet needs and usage of DApps, right? So that's number 1. We put these, and we did this using a Convergent K-Means clustering algorithm. Then we exported these 3 solutions into crosstabs, and we found the solution that had the best story and that helped us the most in terms of product design. And then created a market sizing deliverable and profiles for each of the segments. Finally, In order to extend the analysis, to be able to keep it alive in our organization, we created a typing tool, which is a segment classifier. So for all these new respondents that we survey in the future, we can decide on their segment membership and conduct analyses from there and continue to learn about these segments and further build out their profiles with maybe more quantitative data, but also qualitative data. Thank you.